To panic or not to panic. So how do you decide when you should call panic and when you should return result? When code panics, there's no way to recover. You could call panic for any error situation, whether there's a possible way to recover or not, but then you're making the decision on behalf of the code calling your code that a situation is unrecoverable. When you choose to return a result value, you give the calling code options rather than making the decision for it. The calling code could choose to attempt to recover in a way that's appropriate for its situation, or it could decide that an error value, in this case, is unrecoverable. So it can call panic and turn your recoverable error into an unrecoverable one. So returning result is a good choice, a good default choice when you are defining a function that might fail. In rare situations, it's more appropriate to write code that panics instead of returning a result. Let's explore why it's appropriate to panic in examples, prototype code, and tests. Then we'll discuss situations in which the compiler can't tell that failure is impossible, but you as a human can. The chapter will conclude with some general guidelines on how to decide whether to panic in library code. Examples, prototype code, and tests. When you're writing an example to illustrate some concept, having robust error handling code in the example as well can make the example less clear. In examples, it's understood that a call to a method like unwrap that could panic is meant as a placeholder for the way you'd want your application to handle errors, which can differ based on what the rest of your code is doing. Similarly, the unwrap and expect methods are very handy when prototyping, before you're ready to decide how to handle errors. They leave clear markers in your code for when you're ready to make your program more robust. If a method call fails in a test, you'd want the whole test to fail, even if that method isn't the functionality under test. Because panic is how a test is marked as failure, calling unwrap or expect is exactly what should happen. Cases in which you have more information than the compiler. It would also be appropriate to call unwrap when you have some other logic that ensures the result will have an OK value, but the logic isn't something the compiler understands. You'll still have a result value that you need to handle. Whatever operation you're calling still has the possibility of failing in general, even though it's logically impossible in your particular situation. If you can ensure by manually inspecting the code that you will never have an error variant, it's perfectly acceptable to call unwrap. Here's an example. Use standard net ipaddr. Let home ipaddr equal 127.0.0.1.parse.unwrap. We're creating an ipaddr instance by parsing a hard-coded string. We can see that 127.0.0.1 is a valid IP address, so it's acceptable to use unwrap here. But having a hard-coded valid string doesn't change the return type of the parse method. We still get a result value, and the compiler will still make us handle the result as if the error variant is a possibility, because the compiler isn't smart enough to see that this string is always a valid IP address. If the IP address string came from a user rather than being hard-coded into the program, and therefore did have a possibility of failure, we would definitely want to handle the result in a more robust way instead. Guidelines for error handling. It's advisable to have your code panic when it's possible that your code could end up in a bad state. In this context, a bad state is when some assumption, guarantee, contract, or invariant has been broken, such as when invalid values, contradictory values, or missing values are passed to your code, plus one or more of the following. The bad state is not something that's expected to happen occasionally. Your code after this point needs to... let me read the top one. Okay, hold on. You should have your code panic when some assumption, guarantee, contract, or invariant has been broken, like invalid values, contradictory values, or missing values passed to your code, plus one of these. So panic if the bad state is not something that's expected to happen occasionally, or your code after this point needs to rely on not being in this bad state, or there's not a good way to encode this information in the types you use. If someone calls your code and passes in values that don't make sense, the best choice might be to call panic and alert the person using your library to the bug in their code so they can fix it during development. Similarly, panic is often appropriate if you're calling external code that is out of your control and returns an invalid state that you have no way of fixing. But when failure is expected, it's more appropriate to return a result. Examples include a parser being given malformed data, or an HTTP request returning a status that indicates you have hit a rate limit. In these cases, returning a result indicates that failure is an expected possibility that the calling code must decide how to handle. When your code performs operations on values, your code should verify the values are valid first and panic if the values aren't valid. This is mostly for safety reasons. Attempting to operate on invalid data can expose your code to vulnerabilities. This is the main reason the standard library will call panic if you attempt an out-of-bounds memory access. Trying to access memory that doesn't belong to the current data structure is a common security problem. Functions often have contracts. Their behavior is only guaranteed if the inputs meet a particular requirement. Panicking when the contract is violated makes sense because a contract violation always indicates a caller-side bug, and it's not a kind of error you want the calling code to have to explicitly handle. When a contract is violated, it always indicates a caller-side bug, and that's not the kind of error you want the caller code to have to explicitly handle. In fact, there's no reasonable way for calling code to recover. I'm having a hard time with calling code. Calling code. In fact, there's no reasonable way for calling code to recover. The calling programmers need to fix the code. Contracts for a function, especially when a violation will cause a panic, should be explained in the API documentation for the function. However, having lots of error checks in all your functions would be verbose and annoying. Fortunately, you can use Rust's type system, and thus the type checking the compiler does to do many of the checks for you. If your function has a particular type as a parameter, you can proceed with your code's logic, knowing that the compiler has already ensured you have a valid value. For example, if you have a type rather than an option, your program expects to have something rather than nothing. Okay, for example, if you have a type rather than an option, your program expects to have something rather than nothing. Your code then doesn't have to handle two cases for the sum and none variance. It will only have one case for definitely having a value. Code trying to pass nothing to your function won't compile, so your function doesn't have to check for that case at runtime. Another example is using an unsigned integer type, such as U32, which ensures the parameter is never negative. Creating custom types for validation. Let's take the idea of using Rust's type system to ensure we have a valid value one step further, and look at creating a custom type for validation. Recall the guessing game in Chapter 2, in which our code asked the user to guess a number between 1 and 100. We never validated that the user's guess was between those numbers before checking it against our secret number. We only validated that the guess was positive. In this case, the consequences were not very dire. Our output of too high or too low would still be correct. But it would be a useful enhancement to guide the user toward valid guesses and have different behavior when a user guesses a number that's out of range versus when a user types, for example, letters instead. I'm going to read that sentence again. But it would be a useful enhancement to guide the user toward valid guesses and have different behavior when a user guesses a number that's out of range versus when a user types, for example, letters instead. One way to do this would be to parse the guess as an I32 instead of only a U32 to allow potentially negative numbers, and then add a check for the number being in range, like so. Let guess I32 equal match guess.trim.parse. Okay. Num, return num. Error, wildcard, return continue. If guess is less than 1, or guess is greater than 100, print line, the secret number will be between 1 and 100. Continue. Match guess.compare reference to secret number. The if expression checks whether our value is out of range, tells the user about the problem, and calls continue to start the next iteration of the loop and ask for another guess. After the if expression, we can proceed with comparisons between guess and the secret number, knowing that guess is a value between 1 and 100. But this is not an ideal solution. If it was absolutely critical that the program only operated on values between 1 and 100, and it had many functions with this requirement, having a check like this in every function would be tedious and it might impact performance. Instead, we can make a new type and put the validations in a function to create an instance of the type rather than repeating the validations everywhere. That way, it's safe for functions to use the new type in their signatures and confidently use the values they receive. Listing 910 shows one way to define a guess type that will only create an instance of guess if the new function receives a value between 1 and 100. Pub struct guess, one field, value I32. Implemented for guess, pub function new parameter value I32 return a guess. If value is less than 1 or value is greater than 100, panic. Guess value must be between 1 and 100 got value. Then guess with the value field of value. Public function value reference to self return I32 self.value. A guess type that will only continue with values between 1 and 100. First, we defined a struct named guess that has a field named value that holds an I32. This is where the number will be stored. Then, we implement an associated function named new on guess that creates instances of guess values. The new function is defined to have one parameter named value of type I32 and to return a guess. The code in the body of the new function tells value to make sure it's between 1 and 100. If value doesn't pass this test, we make a panic call, which will alert the programmer who is writing the code that they have a bug they need to fix. Because creating a guess with a value outside this range would violate the contract that guess new is relying on. The conditions in which guess new might panic should be discussed in its public-facing API documentation. We'll cover documentation conventions indicating the possibility of a panic in the API documentation that you should create in Chapter 14. If value does pass the test, we create a new guess with its value field set to the value parameter and return the guess. Next, we implement a method named value that borrows self, doesn't have any other parameters, and returns an I32. This kind of method is sometimes called a getter because its purpose is to get some data from its fields and return it. This public method is necessary because the value field of the guess struct is private. It's important that the value field be private, so code using the guess struct is not allowed to set value directly. Code outside the module must use the guess new function to create an instance of guess, thereby ensuring there's no way for a guess to have a value that hasn't been checked by the conditions in the guess new function. A function that has a parameter or returns only numbers between 1 and 100 could then declare in its signature that it takes or returns a guess rather than an I32 and wouldn't need to do any additional checks in its body. Summary. Rust's error handling features are designed to help you write more robust code. The panic macro signals that your program is in a state it can't handle and lets you tell the process to stop instead of trying to proceed with invalid or incorrect values. The result enum uses Rust's type system to indicate that operations might fail in a way that our code could recover from. You can use result to tell code that calls your code that it needs to handle potential success or failure as well. Using panic and result in the appropriate situations will make your code more reliable in the face of inevitable problems. Now that you've seen useful ways that the standard library uses generics with the option and result enums, we'll talk about how generics work and how you can use them in your code.